I'm standing between you and lunch. I only have 57 slides. Should be fine. I think it's important to highlight this kind of new direction of quantum science. For me, it's exciting to work on it because it's really at the intersection of a lot of fields, and I like to call this quantum science, technology, engineering, and mathematics, or QSTEM. And it's also important to note that computing is not really the only application of this. So say, like, I'm sure many of you have doubts on whether a quantum computer can be built. I'm naturally pessimistic. I'm becoming less pessimistic myself personally, which is new to me. But even if, say, quantum computer doesn't get built, there's a lot of other applications of quantum technologies that seem to be more robust. For example, in communication, sensing, for example, LIGO, and simulating physical systems. Everybody knows that Feynman quote. I'm not going to repeat it. So the quantum stuff is, these kinds of effects that are useful for this are probably here to stay, even if computers don't really make it, even if we can't factor numbers. So in spirit of spontaneous historical slides at this session, I decided to add one of my own. All these technologies are difficult to realize because quantum systems are fragile. And so you need error correction to make them work, communicate across a link or store a quantum memory. And the oldest instance of error detection that I'm aware of is called casting out nines, which is a way to detect errors in multiplication of numbers. Again, the only reason this slide is here because in the spirit of the session, I want to put up pictures of really old people. Apparently this was initially an Arabic procedure, and then it got translated to India. And this is, to my knowledge, the oldest instance of error detection for classical codes, of course, multiplication. All right, so this talk will be about continuous variable system because there's really a kind of a coherent message I can frame around these systems. These are the things you probably learn in your quantum mechanics class. So they're characterized by continuous degrees of freedom, such as position momentum of some mechanical, phononic mode, or quadrature components of electromagnetic field mode, as we've discussed in the previous talk. And there's really kind of the big five, or kind of big five platforms that that are underlied by this kind of math: optical fibers, or free space, vibrations of trapped ions, are harmonic oscillators. Microwave cavities as opposed to optical cavities, also photonic. There's at least three companies actively working in this particular technology. Free electron light interactions, kind of a new player in the field. There's some continuous variable degrees of freedom there. And mechanical, your vibrating drums and vibrating things that are quantized such that their amplitude now becomes resolvable in terms of phonons. So why should you care? Well, for one, we already use these. We communicate via optical fibers all the time. For another thing, whatever your quantum system is that you're building in the lab, it has more than 2 levels to it, most likely. And so those levels are already available to you. And then it makes sense to start asking the question, well, maybe instead of scaling and adding more and more subsystems, we can maybe use more energy per subsystem and get the benefits of that extra redundancy and that extra space. Moreover, some of these, in particular the microwave cavities, admit very long lifetimes, longer than the superconducting qubits themselves, and so that was a very natural reason to start looking at how to encode and process information inside those. Also, the last reason is really just intrinsically kind of, there's a whole different world of continuous things in there, which is just intuitively, intrinsically interesting to study for me as a theorist. So this is kind of the main slide. I like to organize sort of the available state space in terms of these two kind of axes. So on the x-axis is the number of subsystems or devices that you're tensoring up or stacking up. These are your number of superconducting circuits, number of trapped ions, etc. And on the vertical axis is the energy you use per ion or per subsystem. And if you only use the first 2 levels per subsystem, this one and that one, and you just scale up the number of subsystems, then you're in a domain where most people are. This is where your qubit encodings and your qubit-based systems are, okay? So you can go this way and get the thermodynamic limit, et cetera. On the other hand, in the last decade, there's been some developments along this completely perpendicular axis where you stick with one subsystem, so this kind of monolithic subsystem. You don't stack any more of them, but you look at how much you can store and how much you can do inside that single subsystem. So you crank up the energy and you can see how much you can control and utilize this space and its redundancy, say, for storage, for robust storage of information. And these were kind of the reincarnation of these bosonic codes that people studied in the last decade, but they were mostly defined on single mode. And since then, I was in grad school back then, so since then I was motivated by basically figuring out what is here. What are sort of intrinsically multi-mode systems, where n here is bigger than 1, that also use higher energy than just the first 2 levels? Are there interesting things, structures here that combine the benefit of a tensor product space of many factors and of higher lying excited states? Okay. One of the applications is error correction. For error correction, you need redundancy. For redundancy, you need space. So there's 2 ways to get space, and we would likely think that maybe if we use both of them in some nice synergistic fashion, we get good ways to protect this information. But that's not the only application. There's many connections between error correction and condensed matter, many-body physics. And so whenever you start looking at many-body models here, you're naturally opening up possibilities of new phases of quantum matter and new ways to simulate other systems. So I want to stress that, while kind of I have error correction in the back of my head very often, this is really an investigation in many-body physics as well. Okay, so the purpose of this talk is to give you kind of our latest results about finally being able to chart this landscape and provide some structure and objects that can fit inside this multi-mode space. So the first 2 we'll talk about kind of in a way together. These are kind of many-body models and error-correcting codes that are associated with coherent states being placed on a sphere in phase space or on a torus in phase space. Okay? So your phase space of a harmonic oscillator, is everybody familiar with that? Yeah? Okay, good. So think about a multidimensional phase space, and you're putting points on a sphere or on a torus inside it of arbitrary dimension. The points I mentioned that we're going to put, the types of things that we're going to stack on these spheres or put on these spheres, are coherent states. So you've heard of these, right? Right. So they have very nice properties, but I'll just rehash real quick. How do you obtain them? Well, the coherent states are basically classical signals. So if you take a classical signal, expand it in your normal mode basis, which are just quantized but not quantum normal modes, eigenmodes of Laplace's equation in a box, okay? You take a signal, you expand it, and the coefficients of the signal can be complex and E&M, and those are just your coherent states. Okay? These are classical points. And we make them quantum by considering superpositions of these states in order to develop interesting many-body models and error-correcting codes. So the simplest code is this CAT code. You maybe have heard of it. If you haven't, this is a good introduction to it, I hope. It's one which encodes information in a subspace, because quantum information is literally superpositions of things, okay? 0 and 1. And so you're encoding it in a subspace, and the subspace is spanned by a basis. The basis is this coherent state alpha and coherent state minus alpha. That's your simplest code. So what does it do? What does it protect against, right? The codes are supposed to protect against some kind of noise. So this code protects against rotations. Anything that kind of, so you're dephasing in your cavities is basically generated by these random rotations that try to take this guy and rotate it over to this guy, and cause a logical bit flip error. And the way this code protects against those rotations is actually via a Lindblad-Master equation, which you've seen today, that basically stabilizes a double well potential whose minima are exactly these 2 states, alpha and minus alpha. The jump operator or dissipator of this Lindblad-Master equation is a squared minus alpha squared, and your basic property of coherent states tells you that this thing annihilates both alpha and minus alpha because a squared doesn't care about the sign. So this is your kind of canonical double wall potential. That's like canonical in the sense that it's like the simplest one that I could think of in quantum mechanics. And the protection against the small fluctuations in the phase space is done by turning this guy on and continuously stabilizing these two minima and their quantum superpositions. In terms of error correction jargon, you can think of A squared as a sort of stabilizer. I'll just throw that out there in case you want to remember this kind of jargon when you talk to your error correction friends. However, what's bad about this code is that while it protects against rotations and fluctuations in the phase space, it doesn't protect against leakage of particle carriers, leakage of photons outside the cavity. That leakage is basically manifest by this error operator A. So just A is basically you lost a photon in the cavity. And when you act on the coherent states with A, you can see that they spit out alpha here and minus alpha here. And so the environment, if the environment had access to basically probing your system with this A operator, it will be able to sniff out which coherent state you're in because the expectation value of the two coherent states is different. And that gives you a logical, what's called a Z-type error. So the Euclidean motion is X-type noise, and this kind of A is Z-type noise. In this case, this is an uncorrectable error. One person's trash is another person's treasure. That's another way of saying this is a gate, okay? Errors that you can't correct, implement logical operations on your code. And so this, in this case, this is a logical operation because it does a logical Z. And if you, of course, rotate too far, as I said, you're going to get a logical X operation. So if you can implement these in a controlled fashion, then you get a set of logical kind of Pauli type operators on your continuous variable code. So the first objects that we can throw in this multi-mode state space we learned are just spheres. And what they generalize is just these cat codes to higher dimensions. So the cat code that I mentioned is just like 1 point here and 1 point here. You can extend these to protect against loss by including multiple points now per logical 0 and multiple points per logical 1. Here, just 2 points here and 2 points here. Or 3 points and 3 points, or 4, etc. You can get a polygon here that's made up, whose vertices form this constellation of coherent states that are used for the code. And quantum spherical codes, the first object that I was going to tell you about, are just extending this to higher dimension. Okay, that's the take home. And believe it or not, it took 10 years for us to think about how to properly extend these. And in retrospect, it's pretty simple. Why didn't we just put things on a sphere to begin with? Well, we didn't think about it. Anyway, when you put things on a sphere, there's some beautiful kind of compound polytopes here, which can be split into simpler polytopes, like this cube being, vertices are being split into 2 tetrahedra, this dodecahedron being split into 5 tetrahedra, and each of these mini polytopes naturally gives you a constellation to use for a basis state of a logical encoding. Just like the 2 alpha and the minus alpha were used for the cat code. So then in a nutshell, that's really how these spherical codes work. I'm gonna just put them here. Again, I'm putting a sketch of a code on this 2-dimensional torus, keeping in mind that it lies on a sphere that's kind of, this torus sits on, but it's harder to draw a 4-dimensional sphere than it is the torus that is contained in the sphere, so I'm just drawing it on a torus, in order to compare also to the other types of codes that I was going to mention. The second object in this kind of talk, and these are these tiger codes. These are also superpositions of coherent states, but now they're superpositions of a line of coherent states, or in general, a torus of coherent states. So instead of being discrete, this is a continuous superposition. And instead of being on a sphere, here the construction restricts you to a torus. Okay, for those of you who know CSS codes, this is basically a manifestation of homology over the integers. But geometrically, these are just constellations of continuously parametrized lines or tori of coherent states that we call the tiger codes, because they also generalize the cat codes. So I mentioned that we had this kind of fluctuations in the phase space that these codes are designed to protect, and we continuously stabilize them, right, in order to prevent you from moving around too much. This is all true for these codes as well. And in quantum error correction, the way you characterize this is for both of these codes is in terms of the following. Turns out, you probably know this, that the Hilbert-Schmidt overlap, or sorry, the Bra-Ket overlap between two coherent states, an arbitrary number of modes, is related to the Euclidean distance between the actual phase space vectors between the two coherent states. And so, when you're dealing with error correction, you want states to be far enough apart so that fluctuations don't connect them. And so this kind of quantum overlap is just related to the classical overlap between the phase space points. And this allows you to basically teleport what you know about classical error correction and the distance between these kinds of packings on spheres and tori into the quantum world. Okay? And in quantum error correction, when you define what is the minimal fluctuation, what is the minimal movement that I need to do to get from one logical state to the other, that's called the distance. And here you can define a distance just simply in terms of the Euclidean distance between these phase space points, instead of the quantum distance between their corresponding coherent states. So this very kind of universal feature that characterizes the distance between both of these, for both of these classes. That was this kind of X-type Euclidean noise that I mentioned. I also mentioned there's going to be Z-type noise that's manifested by leakage of carriers, leakage of particles out of the system. That is basically determined. So how many photons leak out of which mode is determined by some vector of non-negative integers. And the loss error is what actually provides that kind of action of leaking out. And the protection against loss, or the action of these loss operators on coherent states, as you know, the coherent states are eigenstates of these loss operators. And so what happens is that each coherent state that's in your superposed constellation and your polytope is modulated by the corresponding coefficient that comes out from this operator. And here, some of you mentioned designs in your talk, so I figured I'd mention this. Being a design is actually sufficient to protect against this type of Z-type noise or phase noise. Namely, if you now think of these operators as some tools the environment has to access your code through measuring expectation values in the different logical states, Cj, where j goes from 0, 1, 2, etc., you can see that the expectation value of these, because of this equation, correspond to just averages of these monomials over the constellation of coherent states that's present in this code. And if this constellation, if this set of points on the sphere is a design, then the design condition, by definition, tells you that this average over these points is equal to the average over the whole sphere. And if this is true for all Cj, then all of these are equal because this is independent of j. Which means that the environment, through these kinds of observables, is not able to distinguish which logical state you're in, because all of the expectation values are equal, and so they don't give you a hint on which j is you're mostly dominant on. So in that case, being a design, a spherical design in this case, is sufficient to protect against this type of Z-type noise. Okay. So that's the first two, kind of in a nutshell. What else can you fit? Well, you can fit Euclidean structures like lattices, right, in Rn. And we didn't discover these. These were, these kinds of states were these Gottesman-Kitaev-Preskill states from 20 years ago. But I do want to mention another recent result we had about these being designs. So again, going along the lines of designs, this is basically in a nutshell what designs are. You basically have an easy way to evaluate something that looks hard because it's got a scary integral here. This is just a sum over a finite number of points. And I already mentioned spherical designs, so I'll just brush through this. Designs exist on many different spaces, including this kind of non-manifold structure, like a triangle or a simplex. So the design here are these 3 points, and it turns out averages over these 3 points actually give you, of these polynomials in these 2 coordinates, 2 dimensions, actually equal to the average over this whole triangle. Okay, so very ubiquitous concept, definable in a wide variety of spaces. And what happens now if we go into this continuous variable world? Now we have an infinite dimensional state space. We have your Fock states. We just go on forever. What happens? Well, it turns out that you can parameterize your quantum states, at least their diagonal elements of a density matrix, as points on a simplex. Numbers that add up to 1 and that are between 0 and 1. Okay? And so if you don't have a design on the simplex, then you won't have a design on the full space. And the point here is that we do not have designs on simplices as they blow up to infinity. Why? Because any design on a simplex needs to have some point in the interior of the simplex, namely some point where all the numbers are greater than 0. Let's say we pick the dead center of the simplex. Everything here is 1 over, all the populations here are 1 over d for finite dimensions d. Well, as d goes to infinity, this thing literally dies. So if we are allowed only to use normalizable states, then we do not have the simplex designs for our quantum states. Therefore, we do not have state designs in infinite dimensions. And that also implies by contradiction that we don't have unitary designs, because if we did, we would have an orbit that would be a state design. So what needs to happen is, put simply, just to remove this normalization and consider states that are outside of that are not normalizable states. But if you're familiar with continuous variables, this is not a crazy thing, because things like homodyne detection use states that are not normalizable. So this is pretty conventional in continuous variable. The main result that I wanted to mention recently is that we actually learned that lattices form, so points in a lattice, superposed in a lattice, that goes on forever, are exactly one such example of a non-normalizable state. So they fit the bill for potentially being used as designs. Well, it turns out that if we take all lattices and we consider states of points of all possible lambda, that set forms a design. And the design here that condition that I want to show is that basically what you want this sum over all possible lattices to equal is the projector onto the symmetric subspace of 2 modes. So the design condition I'm doing is not using an integral over all states, because that's very tricky to define. Instead, I'm going to go straight to the group theory for those of you familiar and just use the projector right immediately in the definition. So anyway, this is what you want, and we're doing coherent states. So we do this integral, and for any coherent state bracket here, alpha 1, alpha 2, we want these two to be equal. So we're going to show that these lattices form a 2 design. There's a 2 here instead of a 3, etc. This is the 2 design condition. And what's crazy about this paper is it was like literally a 3-line proof. So for one, we only want to show equality of these, and all we need is to use diagonal matrix elements, because coherent states behave like that. You don't need off-diagonal elements to show equality between 2 matrices in the coherent state basis. So for one, we only use diagonals here. And for the second thing, it's literally 3 steps. So we're doing this integral, we want to get this. Okay, so first we get rid of all the shifts that all the lattices can have. So each lattice can be shifted along the unit cell, like to a point inside its unit cell to give you a shifted version of it. We do that integral, it's a Gaussian integral, we get this thing. Now we have this insane looking integral, we simplify it, and so we're still stuck with this weird integral over all lattices. Well, it turns out there's some very smart math papers that basically say this is actually equal to a Gaussian integral, like to an integral over just the phase space. And so this is the one non-trivial step in the paper, and once you get rid of this insane looking integral and you just have an integral over beta, then you're reduced again to a Gaussian integral, and you show, from what you can remember, the exponential of the Euclidean overlap, which is exactly equal to the quantum state space overlap from the previous slide. Okay. So anyway, the long story short here is that if you have these kinds of displaced GKP states integrated over all possible lattices, this is a way to realize a 2 design on infinite dimensional space. And there's tomographic applications thereof of this that I won't cover, but just to summarize, these things are pretty useful. All right, so that's the third. So one more and then lunch. Okay. So this is, so what else can you fit in this space in Rn? Well, you can fit simplices in Rn. So simplices are like a line and a triangle, equilateral triangle, pyramid. These are all called simplices. And the structure we study for this 4th result is what's called a discretized simplex. So I guess I made that up, but it's a natural definition, because you just cut the simplex up into little pieces, and you put points on the little pieces. So you do a little scaffolding, right? Okay. So in 1 dimension, these are that. So you mentioned 1, 0, 0, 1 constant excitation space. So there you go. There's your 2 states. And I already hinted at what these simplices are meant to model. In 2 dimensions, these are going to be triangles. In 3, these are going to be pyramids. And these abstract structures are actually very useful because they kill 3 birds with 1 stone. For 1, they describe directly constant excitation spaces of Fock states of Q modes. So here, we had a constant excitation space of 2 modes. We had 1 excitation split around 2 modes. What are the 2 ways to do that? There's only 2, 0, 1, 1, 0. Put the excitation in the first or the second mode. If we have 2 excitations, there's 3 ways to do it. 3 excitations, there's 4, etc. If we have 3 modes and 1 excitation, there's 3 ways to put it, and then etc. Here's your 3 mode states. 4 modes, it's going to be the pyramid, etc. Okay? So these numbers are literally telling you the number of excitations in a given Fock state that corresponds to a vertex of a discretized simplex. Okay, so we have a model for the state space and the corresponding geometry for this state space that's actually respected by operators that cause you to lose and gain photons. So we can again design error correcting codes for these spaces by utilizing packings on triangles and cooking up constellations and superpositions. Am I out of time?
Yeah.
Okay. So I'll do one example and then I'm done. So what you start with here is you pick now a constellation of points on the simplex. And it turns out that there's classical codes that's been developed for this for a long time ago. But then the tricky part is how to pick a quantum code out of these points. Which points to superpose to get a quantum code? Before, I was using polytopes. I was saying this cube can be split into 2 tetrahedra, and I can use the tetrahedra for the 2 codes. But now I have no ways to partition these points. Well, it turns out there's a very general procedure called Terburg's theorem that under certain conditions gives you automatically a partition of these points. And so I now, given this cranking out this Terburg machine, I can cut up these classical code points, these packings, into different colors and superpose the different colors to get logical quantum code words. And in the Fock space, there's an example for this, say, 3-mode code, where the red guys are the 3, 0, 0 states, and the one guy in the center is the 1, 1, 1 state. This gives you this existing code as a simple example. And then I mentioned we kill 3 birds with 1 stone. Here's the other bird. Turns out these labels also correspond to Dicke states. Namely, these labels form what's called the composition of the Dicke state. The 3 tells you the number of zeros in the Dicke state, 0 tells you the number of 1s, and the 0 tells you the number of 2s. So this state here corresponds to this state here. This one is this one, and this one is all of these, because all of these have the same composition, 1, 1, 1, 0, 1, 2. So we automatically, giving a quantum code on this constant excitation Fock space, we automatically get a permutation invariant code whose code words are spanned by Dicke states. So those are 2 of the birds. So that's basically it. I want to thank my students and collaborators for basically doing all the work. These guys were the lattice collaboration, and Arda here recently presented this at QIP. With that, I guess I want to wrap up and thank you for your attention. And also thank you for the wonderful conference and the invitation and the honor to be able to close it and no longer stop you from having lunch. So yeah, thank you.
Thanks for the nice talk, very nice questions. I have a question. You started with the superposition of coherent states, and coherent state you can describe with real and imaginary numbers, right? Mm-hmm. And then it's clear for me that can be put in a 2-dimensional plot. And in the end, we came up with a 3-dimensional structure. Mm-hmm. How can you?
So this was a 1-mode coherent state. And then when I was using bold, so when I'm extending to multiple dimensions, I'm using a vector of complex numbers to denote the coherent state. So this is a vector alpha 1, comma alpha 2, comma alpha 3, comma alpha ... alpha n. So n-mode coherent states.
Any modes?
N-mode, yes.
Ah, okay.
Higher dimensional, yeah.
Okay, good. Thanks.
Yeah, otherwise you can't fit like a 4-dimensional polytope into one mode, because that's only a 2-dimensional space, but the polytope is 4 dimensions. So you need 2 modes,
Okay.
right? 7 dimensions, you need 4 modes.
Yes, I got it.
Yeah.
Thanks.
Yeah, thanks for the great talk, Victor. Can you maybe tell us a bit more about these CV designs? I mean, in the end, wasn't it like super difficult to construct designs in CV spaces to begin with? Now it looks very easy.
Well, it depends on who's speaking and whether I'm actually saying technically rigorous and correct statements. My student basically proved the non-existence of these things using some remote theorem in some analysis book that he found. But for me, the simplest explanation, like kind of what I kind of came out of that, for me, is just the fact that you need to remove normalizability. And as soon as you do that, you know, you're still able to integrate outer products of things that are, even though their inner products are infinite, you can still integrate their outer products. Again, homodyne detection. This is not some completely crazy statement. You can do that. And so once you remove normalizability, you have the possibility of doing this, and then we just had a simple guess for what these should be, and it turned out that they were fine. And they were literally just one of the elements of the design. Our initial design is this thing without the 1/d. A simplex thing that's like just doesn't die off. What's interesting about these is these are a bit more physical and natural, and so now, and they form an infinite family. So for arbitrary numbers of modes. So this is the first infinite family of designs.
Cool.
Yeah.
Well, we have time for just one more question. Well, or perhaps two.
Thank you for a great talk. I just have a follow-up question. Can you comment what happens if you put energy constraints? Like, I guess you can still define this type of objects. Like, is it efficient, trivial? Like,
yeah, no, it's good. It's nice. So what you do is you just dampen this thing. So this is some matrix of 1s and 0s on the diagonal, and with increasing number of Fock state number. So you just put in a thermal cutoff on the diagonals. And then given that fixed temperature, you say, okay, well, I want my states to be equal to that for fixed temperature. Okay, now your states are allowed to be normalizable because everything is now converging and doesn't blow up. And so you can also similarly dampen these states with the thermal factor, and you get these things we called regularized designs. And the equality kind of holds between kind of these regularized versions of these things. And yeah, anything that basically, what those allow you to do is do kind of similar tomographic applications for states that have energy less than the energy of the thermal state that you use to damp everything.
great. Thanks.
One more question.
Yeah, thanks for the nice talk. Can you maybe briefly comment on the noise robustness of these new codes when you scale them up, for instance, and or maybe also on gates, on how to do them?
Right. So gates, the gates that you do for these are these Euclidean. Basically, if you have a way to rotate this line into that line, there's your gate, or these points into that point. So for like these polytope kind of codes, it's very simple to see. If you just take your cube, you flip it, then the red and the yellow get exchanged, so that's a logical X gate, for example. So those are fault tolerant kind of X-type gates. And then Z-type gates are going to can be dissipatively basically implemented, and they consist of these like leading order uncorrectable errors. If you can somehow implement these, there's ways to do that. Implement these monomials, and they will give you Z-type gates.
Okay, thanks. Yep.
There's more. There's a lot more we can chat offline.
Well, let's thank the speaker again.